Hello and welcome to Chapter 4, Section 6, Part 2. Today we are still doing integrations with fractions, but we're going to throw in some change of variables now and there. This is something that you've seen before, just now we're kind of complicating things a bit more. That's all. So here we go. First example. Alright, so for this problem we've got a fraction, obviously, and then also on the bottom we have like x plus 1 squared. So in the past what we would always do is try to like FOIL this out and then hope that whatever its derivative was, we could use that as u, and then the derivative would match the top or something like that. Well, for this problem, it doesn't quite work as well, and also I really don't want to FOIL it out. So for this problem, I'm going to use u equals x plus 1. That way, I can just write this bottom part as like u squared, and then du would just be 1 dx, so dx really just equals du. Okay, so then on top though, we still have this 2x there, which is awkward because our derivatives doesn't really match it. So the change of variables part is going to be where I rewrite my u into terms of x. So if I subtract 1 on both sides, I end up with x equals u minus 1. So now if I rewrite my original problem, it'll be 2 times, and instead of x, it'll be u minus 1 over, and then on the bottom we can write the x plus 1 as u squared, and then dx we said was equal to du. So now our problem looks like this. And now this is much easier to do because I've got this 2 here, which is just a constant, so we can move the 2 out front. So that leaves me with u minus 1 over u squared du. And then because now I still have a fraction, but I only have one term on the bottom now, I can actually split this up into multiple fractions. So as long as you only have one term on the bottom, you're allowed to split the fractions. So I can go u over u squared minus 1 over u squared. So then u over u squared is just 1 over u minus u to the negative 2 du. And we talked about last time where the integral of 1 over u is just ln, the natural log of u. So I'm going to write the 2 in front. We have the natural log of u, technically absolute value of u, minus, and then u to the negative 2 power we can use the power rule for. So this will end up being u to the negative first over negative 1 power, and then plus c at the end. All right, and then we just got to plug our u back into our original equation. So it'll end up being 2 times ln of x plus 1, absolute value, minus, or well, plus, because we have minus and then a negative 1 on the bottom. So this u to the negative 1 power will turn into 1 over x plus 1 plus c. And then just kind of distributing out that 2, I'm just going to rewrite this as 2 ln absolute value of x plus 1 plus 2 over x plus 1 plus c, and that's my final answer. Alright, this next example is similar. So we have the integral of x over 2 minus 3x squared dx. So just like last time, we know that on the bottom, technically we can FOIL this out, but then even if I FOIL it out, when I take the derivative, its derivative is not what's going to be on top. So change of variables will be the best thing here. And so I want to use u as like whatever's inside the parentheses, so that 2 minus 3x. Du would end up being negative 3 dx, and so dx equals du over negative 3. All right, but then when I rewrite my original equation, I'm going to need to rewrite everything in terms of x, or my u in terms of x. So I can subtract 2 on both sides and then divide by negative 3 to get x by itself. All right, so my original problem now is going to look like this. U minus 2 over negative 3 instead of x over u squared, and then dx would end up being du over negative 3. Okay. So right now I have like fractions on top of fractions, and I don't like that. So let me just rewrite it as u minus 2 over negative 3. And then instead of dividing by u squared, this is the same as multiplying by 1 over u squared. All right, this looks much nicer. So it also looks like if I multiply this out, I can take out a constant of 1/9 because of the -3 on the bottom of two fractions. And then the integral of u minus 2 over u squared du. Okay, just like before, since I only have one term on the bottom of the fraction, I can split this up into two separate fractions. So u over u squared minus 2 over u squared. So really this is, if I simplify this, 1 over u minus 2u to the -2 du, and then I can integrate. So 1 over u would be ln of u minus 2u to the -1 over -1. Plus c at the end. All right, and then this is the part where we want to plug in our u. So this u should be 2 minus 3x, absolute value. And then I'm just going to simplify this out. So the negative will turn into a positive. 2u to the -1 would be over 2 minus 3x plus c. And then we just got to multiply all of that by 1/9. So it'll be 1/9 natural log of 2 minus 3x plus 2 over 9 times 2 minus 3x. That'll do it. Alrighty. There we go. Not too crazy. It's just that change of variable part is once you have that going, then it kind of makes the rest of the problem easier. But being able to recognize when you need to use it, that's probably the hardest part. But in general, that's why we need to know our derivatives pretty well, because if I know like 2 minus 3x, the derivative is -3, so when it's just a constant, it's much easier to do versus if I were to FOIL it out and then find the derivative, it'd be more complicated. All right, with my next example, I want to do some with trig. So here we go. I have fractions, so great. I know I'm going to need to use u sub. For here, because I know my derivatives, I want to use u as cotangent x, because knowing my derivatives, the derivative of cotangent x is negative cosecant squared x. Okay, so when you know your derivatives, that's when it's a lot easier to recognize what to use for u. And once I know that the derivative is negative cosecant squared, that's already on top. We just have the negative in front that's different, but that's just a constant. We can deal with that easily. So our dx here is going to be du over negative cosecant squared x, so that when we rewrite our original problem, this will cancel out. So we have cosecant squared x over u times du over negative cosecant squared x. Okay, so really we can take out the -1, and then we end up with 1 over u du, which is just negative natural log of the absolute value of u plus c. And then plugging u back in, we have the negative natural log of cotangent x plus c. Not too bad, but it does definitely help to know your derivative rules. Okay, let's do another one. So this time, let's do the integral of tangent of x dx. Oh my gosh. So first, taking this as is, tangent of x, we want to figure out like what can I take the derivative of to get just tangent. And I don't think there's anything that exists like that. So instead, let's rewrite this so that it makes it a little bit easier for ourselves. Because tangent can also be written as sine x over cosine x. So now I know it's weird because I'm complicating it into a fraction. But if I make it a fraction, then at this point I know the derivative of sine is cosine, so that's nice. The derivative of cosine is sine, or negative sine. So, I mean, it's all in there. So that's kind of nice. So for this problem though, because I know when we usually try to cancel things out with the whole like rewriting the du with the dx thing, we end up dividing by whatever it is. So usually we want the thing that's on the bottom of the fraction to be u. So while the derivative of sine is just straight up cosine, which is already in there, it won't actually end up canceling out. So for this problem, we're going to use u equals cosine. So du is going to be negative sine x dx, and so dx will be du over negative sine. Okay, so now rewriting that original problem, we have sine x over u times du over negative sine x, which gives us a negative 1 that we can take out, integral of 1 over u du. So the integral of 1 over u, we've been saying all along, is the natural log of the absolute value of u plus c, and then we have that negative in front. So replacing u with cosine x, that would be it. All right, one last example. So here, I'm just trying to throw in some tangents and e's at the same time. So for this problem, we want to figure out what to use for u first. So knowing the tangent is going to be like similar to the last problem maybe, because we just did a tangent problem, but we also have an e in there. But e's are kind of nice because like the derivative is just itself, so that kind of helps. Keep in mind when we take tangent of something, like it's all of that e to the 2x, so that kind of gives us a hint, like because it's inside the parentheses. So let's try using u equals e to the 2x. When I find the derivative of that, we need chain rule because we've got e to the something more complicated. So the derivative of the inside would be 2x. So the derivative of the inside would be 2, and then the derivative of the outside would just be e to the 2x power. So dx would be du over 2e to the 2x power. And that's also nice because the e to the 2x power is already part of our original problem. So rewriting this now, we have e to the 2x times tangent of u, and then instead of dx, it'll be du over 2e to the 2x power, which is nice because things cancel. And then we can rewrite this as 1 over 2 on the outside because of that 2 from the du over whatever, leaving us with just tangent of u du on the inside. And we just found the integral of tangent of x, so tangent of u should be the same integral as before. So I have that half in front, but then I know the integral should be negative natural log of cosine of u this time instead of x, plus c. Okay, and then we just need to plug the u back in. So this would be cosine, and then u was e to the 2x power plus c. So just making this nicer, negative 1/2 natural log cosine of e to the 2x plus c would be our final answer. Okay, that's it for the new stuff in this section. Thanks for watching. Hope this was short and quick for you. Don't forget to like and subscribe. See you next time.